This video focuses on Chapter 10, the properties of gases. First of all, our definition for a gas. It's a substance that has no well-defined boundaries, so no fixed volume or fixed shape, but diffuses or spreads out rapidly to fill any container in which it is placed. Conditions to be aware of are temperature, which affects the kinetic energy of the molecules. Increasing the temperature means increasing the movement of the molecules. Pressure is all about how many collisions there are per second with the walls of the container. You can compare the two of these here. We can see this container must have a higher pressure because there's more collisions with the walls of the container. Volume is about the amount of space that the gas molecules have to diffuse into. Large volume here on the left, smaller volume here on the right, and that becomes important when we're discussing how the gas particles interact with each other and how frequently they collide with each other. In this chapter, we're going to be dealing exclusively with the Kelvin scale when we're discussing temperatures. So on the scale here, you can see that 0 degrees Celsius is equal to 273 degrees Kelvin. Our Celsius scale is based around the freezing point and boiling point of water. However, the Kelvin scale is all based on absolute zero. The theoretical or the theory behind absolute zero is that this is where the temperature would be so low that the gas molecules would be moving so little or hardly at all that they would effectively occupy zero volume. Pressure is equal to force over area, which would give us the units of Newton per meter squared. This can be simplified and just called a Pascal. Normal atmospheric pressure is 1 times 10 to the power of 5 pascals, and since we have quite a large number here, we usually use the unit of kilopascal instead, where 1 kilopascal would be equal to 1,000 pascals. And our units of volume can be given in cubic meters or cubic centimeters. And the conversion for these is shown here, and when we get to the end of that, 1 meter cubed is equal to 10 to the power of 6 centimeters cubed, so multiplying by 1 million. Standard temperature and pressure. Temperature in Kelvin would be 273 Kelvin or 0 degrees Celsius, and pressure would be 100 kilopascals. It's actually closer to 101 kilopascals, but to simplify calculations in the Leaving Cert, they tend to use the value 100. So, looking at these gases, they all have different physical and chemical properties, but there are 5 laws which they all obey. So we're going to go through those now. First of all, Boyle's law. This states that at a constant temperature, the volume of a fixed mass of gas is inversely proportional to its pressure. So fixed mass here, that's just to make it a fair test to keep it consistent. And since we are looking at the relationship between volume and pressure, we are going to keep our third variable constant. So temperature is not going to change here. As we mentioned before, pressure is due to collisions with the side of the container. If we want to increase the pressure, that means we have to decrease the volume. This brings the particles closer together, causing more collisions with each other and with the sides of the container. You can see that in this animation here. On the left, we've got a low volume and a very high pressure. There's loads and loads, too many to count. Collisions happening there. On the right though, we have a much larger volume, and you can see that there are far fewer collisions between the gas molecules and the side of the container. This means that volume is inversely proportional to pressure. As one increases, the other decreases. It can be shown writing the symbols out using alpha for meaning proportional. Volume is proportional to 1 over pressure. If we want to make that an equal sign, we can do that by multiplying 1 over P by K, a constant. Rearranging that, we're saying that volume multiplied by pressure is equal to a constant value. If I give you a value and a volume and a pressure value here, if I give you a volume of 10 centimeters cubed and a pressure of 100 kilopascals, my value for K there, V multiplied by P, would be 1000. This becomes useful when you're given another set of conditions. If I said to you that the volume was now changing to 20 centimeters cubed, and work out the pressure for me, you would know that its volume multiplied by pressure values are equal to 1000. So you can work out the pressure by doing 1000 divided by 20, which will give you 50 kilopascals. Same way as it would work if I gave you a pressure of 200 and asked you to find the volume. The constant, again, when you multiply the two values together, is going to be 1000. So my value for volume must be 5 centimeters cubed this time. We can put that all together and eliminate the K value, the need for the K value, by looking at this equation. I can multiply together the values for one set of conditions, and they will be equal to the values multiplied together for any second set of conditions. And that way, if I'm given 3 bits of those information, I can arrange my equation and solve for the other one. The second law is Charles's law. This time we're keeping the pressure constant, so we're not going to change the pressure. We're looking at the relationship between volume and temperature. And Charles's law is that the volume of a fixed mass of gas is directly proportional to its temperature on the Kelvin scale. Now, you may have been distracted by the animation on the right there while I was talking. What you'll see is that as we increase temperature, volume is increased as well. So they're directly proportional. As one increases, the other increases with it. This can be written using our alpha symbol again. Volume is directly proportional to temperature, and we can bring a constant in here to get our equal sign. And this time, rearranging that, we get that volume divided by temperature is equal to a constant. So that the volume and temperature at one set of conditions is equal to the volume divided by the temperature at another set of conditions. The third law then is putting these two laws together to give us the general gas law. We combine Boyle's law and Charles' law to give us P1V1 over T1 is equal to P2V2 over T2. 2 rules to obey here. All of your temperatures must be converted to Kelvin, and units on either side must be consistent for volume and pressure. It doesn't matter whether you use pascals or kilopascals, as long as the pressure unit on both sides is in the same unit. The same for volume. You can use centimeters cubed or meters cubed as long as you're using the same on both sides. Let's go through an example of this type of calculation then. So the information we're given is that a sample of nitrogen gas has a volume of 75 centimeters cubed and at a temperature of 27 degrees Celsius and a pressure of 95 kilopascals. Find the volume that the gas would have at STP. So our first set of measurements are the ones highlighted there. They're given in the question. What you'll notice though is that we've been given degrees Celsius for temperature. So we must add 273 to that to convert it to Kelvin. And that gives me my values for P1, V1 and T1. Next, it says find the volume that the gas would have at STP. We know that the values for standard temperature and pressure are as shown here, and we have one unknown, which is the volume. So we take our equation, P1V1 over T1 equals P2V2 over T2, and we substitute in all these values. We've seen equations like this before for volume and molarity, so hopefully the rearranging of them isn't too new to you, but if you need me to go over that in another video, I can. We rearrange this and we get a value for the volume at 64.8375 centimeters cubed. Now, if we just take a look at that for a second, our pressure has gone from 95 to 100. So our pressure has increased and our temperature has decreased. So the pressure has increased, temperature has decreased, so the volume also had to decrease to counteract those changes.